Hey everybody, welcome back to Young Engineers of Today. Um, well, I know all you guys. Uh, all of you were here last semester. I think. Hey Mateo, hey Caleb, welcome back. Well, actually, two Calebs. I believe we only had one Caleb last semester. Well, I'll go through the introductory slideshow. It does spend some time, like a couple of slides talking about what we're going to be going over this semester. So that'll be good for those of you who've been here last semester. Um, Otherwise, this is going to be a very, very familiar looking presentation, and I apologize. I am dealing with the flu right now, so I'm not an incredibly interesting person. I'm not my normal hyperactive and bright and shiny self, but regardless, we'll get through this together. And you guys will get a nice little snapshot of what we're going to be doing this semester. It should be some pretty cool stuff. So we'll go through it, and hopefully you guys will at least find some parts of this enlightening and interesting. Um, but yeah, again, I apologize. I do not feel 100% right now, but we'll get through this, and it'll be a pretty easy class today anyway, since it's just the introductory thing. Next week we'll actually get started on doing stuff and learning new things and all that exciting stuff. So, hmm, with that in mind, let's go ahead and get this show started. So, do you like to take things apart? Just here's some questions for you guys. Would you find building a game at least as fun as playing the game? I think you guys probably remember my opinion on that. If you find it more fun than playing the game, then, well, that's cool too. But if you find it at least as fun, then I think you're still definitely in the clear though. Hey Cohen, how's it going? Welcome back. Are you curious about how to use solder or epoxy? Are you curious about how to repair a tent with needle and thread? Excellent, glad to hear it. Do you enjoy math or science? Do you read science fiction or fantasy? Not the tent thing? Yeah, I get you. Yeah, we don't really cover the tent thing. I don't think we ever have in Young Engineers. But hey, you know, at some point, yeah, you'd be able to do that. If you answered yes to any or most or all of these things, welcome. You're among friends and other like-minded people. And I think that's an important thing to establish. Uh, because sometimes it may not feel like it, but I want to let you guys know you're not alone. You got other people who feel the same way. Certainly I do. We're all reasonably cool people as I understand it, so, shouldn't be too terrible. But yeah, welcome. We're all in this together. Um, I was going to say something, but I totally lost it. Anyway, what does the structure of this look like? Well, again, those of you who have been here already, those of you who are here for the fall semester, or perhaps the spring semester before that, are already pretty familiar with how this is structured. You're going to learn by doing. So there's going to be some times where I'm just sort of talking at the computer and gesticulating wildly, although you can't see it, and, drawing things in paint uh, terribly. Um, but there will also be times, as you guys, I'm sure, remember if you were here, where you did stuff alongside me. I would tell you guys how to do something and be like, okay, you should do this too, kind of a thing. So we try and keep it, and certainly in the labs, you're going to be spending a lot of time doing stuff with your hands as well. You will work towards being a technology creator, not just a consumer of technology. Not that there's anything wrong with being excited about technology, but sometimes knowing about how it works underneath the hood makes it even more exciting. You don't take it for granted. You understand it. You have, you have sort of an agreement with it. It you might know how to fix it in case things go wrong. You might be more inclined to take good care of it. That sort of thing. Like, how many of you have dealt with people who are like, oh, this computer's terrible, it's so slow and it's so bad. And then if you take a look at it, it's filled with all kinds of, malware and, downloaded toolbars and there's, running Internet Explorer and they're just like, oh, this computer is so old. And it's like, it's only a year old. You just aren't treating it right. But there's that difference in thinking. If you understand how it works underneath the hood, you understand that it's not necessarily the computer's fault that it's like that. It's not necessarily a poor uh, piece of technology. Sometimes they are, but not always. And also you know how to fix it so it could last longer. Whereas if you didn't have that understanding and you were just doing things that were detrimental to it, and one day you woke up and it took 5 minutes to load up Internet Explorer and you'd just be like, this is terrible, this thing sucks. Um, so there is sort of a respect gained for a lot of these things once you understand what exactly is going on and why it does the things that it does. Anyway, how are these classes going to be structured? Well, they're going to be class meetings. 1 hour labs twice a week online. Those are your time with me. Um, sometimes they're kind of a lecture format. Sometimes they're more of a follow along kind of format. But that's going to be pretty much the bulk of your time with young engineers. So I'm sorry to say you're stuck with me. Um, certainly for the next couple of months online. But yeah, that's going to be the bulk of your time with young engineers is on the computer. And then they're also going, oh, yeah, I forgot about this part. No homework. Um, I might ask you to do something for, uh, no, we did have to, yeah, never mind. I might ask you to do something for, the next class, like, hey, can you have this downloaded? Kind of a thing. Um, or can you set this up for next class? But I'm not going to grade you on it because that's not the purpose. Purpose of this is not to give you a whole bunch of information so that you can, return it to, like, regurgitate it to me in either a homework assignment or a test. The point is to expose you guys to different branches of engineering and different areas of knowledge and hopefully foster some sort of interest in you so that you can pursue it if you're so inclined. But it kind of defeats the purpose if I'm sitting there going like, hey, what do you think, uh, what happened in 1492? Um, because that's not the purpose of this. It's if there's something that you don't personally find interesting, which I'm sure happened to you guys last semester, that's okay. That's totally okay. Just power through it with me. We'll move on to a new subject before it's too long. Hopefully that one will be of interest. But I'm not going to force you guys to try and at least, feign interest in something because that makes it worse as well. So no tests, no homework because that's just not how this operates. There will potentially, however, be a digital portfolio. I know I sort of harped about it early on in the fall, and then nothing came of it. Um, that's just one of those things. Uh, I'm not gonna keep on your guys' case about it necessarily. I'm gonna give you guys the tools for it, and then if you're so inclined, you can add your own sort of personal stuff to the digital portfolio. Um, but again, if I make you guys do something, even if I'm not grading it, like make you put something into your digital portfolio, it does sort of veer towards homework, which, to be fair, it's not like I'm afraid of the stuff. Um, I do encourage you guys to work hard, and if you find something interesting, run with it and continue doing it, even when it starts becoming difficult, because even if you find something interesting, even if you found the thing that you want to do for the rest of your life, it's not always going to be fun 100% of the time. Sometimes it's going to be hard work, and it's going to be annoying, and you're going to feel like you're throwing your head up against a wall. And that's just kind of how life is. So, when you get right down to it, when you guys are pursuing whatever you're interested in, you're going to have to put a lot of work into it anyway. Um, so, I'm not gonna make you necessarily do anything. There's also going to be in-person lab sessions, as you guys well know. 1 2-hour lab every other week on Thursdays. At least it was in the past. And then Saturday labs for those outside of Charlotte or who cannot come on the Thursday, the regularly scheduled Thursday one. But the kinds of stuff we'll cover. There's a ShotBot Gatling rubber band gun. If that's not your cup of tea, I know that Mr. Dubik has another project cooked up that you could work on at the same time. So it's not like you'd be sitting there twiddling your thumbs or whatever. But a Gatling gun that shoots rubber bands, that's kind of neato. Precursor to like the minigun and the machine gun, it's a gun that has several rotating barrels. Each, when a barrel rotates in position to the firing chamber, then a bullet is fired off, or in this case, a rubber band. Yeah, yeah, exactly. Um, Using the other mill to make an Arduino. There's also going to be cybersecurity and then custom multi-stage model rockets. So you guys are going to be doing some pretty neat stuff. Yeah, death by rubber bands. First off, I'm pretty sure everybody knows how to raise their virtual hand, but just in case you want to test out the equipment, feel free. Yep, look at that. Hands going up. Excellent. No surprise there. Make sure you've registered for all the webinars, at least all the ones that we've got scheduled so far, just so you can get the emails and you can sign up and everything like that. Uh, yeah, there's that. Have you registered on Edmodo? Don't really use it all that often, but I do believe that there was one instance last semester where I was running into technical difficulties, and so I sent out a notice on Edmodo that I wasn't going to be able to teach the class. Um, on top of that, though, it's a good place to communicate with the other people in the class. Now, I don't have Edmodo codes yet. Um, Hopefully, I should get those soon. In which case, we can maybe spend Monday getting everybody situated with Edmodo. You may have received an email with an Edmodo code in it. I'm not entirely sure, but we'll figure it out. And then, have you created your Gmail account? I believe everybody here should have already. But yeah, that's for your web space for the digital portfolio and all that stuff. And then you got to make sure to subscribe to the YouTube channel for webinars. Be sure your parents are okay with it. I know you guys probably are subscribed to a dozen YouTube channels without your parents' permission, or at least, whatever. But regardless, I ain't going to step on any toes here. If it's a good idea to check first, then you go ahead and check first. I'm not going to make anybody, do anything. And ask your parents to like us on Facebook so they can stay up with everything going on using Facebook. So they can like the Young Engineers of Today webpage, Facebook, or page on Facebook, and then there will be updates and stuff like that posted there. So now we get into what is an engineer? Well, you guys already know this. It's the practical, well, here's the dictionary definition. The practical application of science and math is in the design and construction of machines, vehicles, structures, roads, and systems. Yeah, train engineer. There's that too. Essentially, engineers use math and science to improve the world, or they drive trains. So what makes a good engineer? Well, engineers need to be strong in math and science. They need to be problem solvers who show perseverance. Need to be able to work as a team and to communicate effectively. So they need to be strong in math and science. Yes, engineering is the application of math and science principles. Because of this, it is essential engineers have a strong foundation in the two subjects. And all engineers, from bridge builders to chemical manufacturers, need to study hard in math or science class. However, this doesn't mean you need to be a math or science superstar. Different positions do require different expertise. And I'll say this right now, I struggled with this when I was younger. Some of you might be saying like, oh, I don't know if this is for me. Like, I'm just not a mathematically inclined person. Like me and math, it's like oil and water. We don't get along, haha. I didn't actually say that specifically, and I don't think anybody who's your age says that. But anyway, yeah, and most of you probably don't have that problem at all if you're in young engineers of today. But just in case, I wanted to let you know this. That's not how it works. People aren't just bad at math forever. People don't just have brains that are incompatible with math. Certainly, some people have a harder time with it than others, but the important thing is to get familiar with math, to get acquainted with it, to understand what's going on, why you do the things you do and all that kind of stuff. Because a lot of times people who don't enjoy math or think that they're no good at math are just told to memorize a certain amount of things, and then that's just how it is. That's just how math is. But there's a lot of logic involved in math, and it's actually fairly interesting. And if you can get comfortable with that, then you can get to be a mathematically minded person, and it's pretty interesting. Math does a lot of cool stuff too. There's a lot of weird and strange ways that numbers interact that people just spend years and years and years researching how numbers interact. Welcome to theoretical math. But yeah, so don't think that you're not like a mathematically inclined person. It's just you and math got off on the wrong foot, but the door is still wide open. But it doesn't mean you need to have to work at it, just like everybody else. You need to be able to work as a team and communicate effectively. This is true. To solve great problems, engineers of different backgrounds must come together to combine their expertise. In order for the team to be successful, you need to be able not just know the answer, but share it in a clear way others will be able to understand. So, if you have an answer for something, but you don't communicate it effectively, if you're in a group with other people and they don't have an answer that's as good or you feel like as effective, but they are able to explain it more clearly, and you go like, no, but that's wrong because it's wrong, and people go, well, why is it wrong? And you're like, because it just is. Unfortunately, at some point, people are just going to decide to go with the less optimal answer because they understand it better, and that's not because people are necessarily dumb or anything like that. It's just because you go with what you know. So you got to be able to communicate your ideas effectively in order to be able to work in a group. On top of that, communication is great because you can start building relationships with people in the industry, getting to know people, making friends, mentors, things like that. Because if you're ever in a position where it comes down to, like you're applying for a job and it comes down to you and somebody else, if the person hiring knows you, they're probably going to hire you. If they know the other person, well, they're probably going to hire the other person. If they don't know either of you, then it comes down to, they have to go through the interview process and, look at everybody's qualifications and stuff like that. But assuming you're not like grossly underqualified for a job that you're, applying for, if the person hiring knows who you are, they're going to be more comfortable with hiring you over somebody else they don't know. And of course, there's this silly little comic about the differences in communication. Sometimes the customer doesn't even know what they want, and then it's sort of like a game of telephone as everybody passes that information along to different people, the analyst and the designer and the programmer and everything like that. They need to be problem solvers who show perseverance. Engineers are presented with huge problems that they need to break down into manageable tasks. They are technical puzzle solvers. It's true. Take something like build a spaceship that goes into space and comes back. That sounds, well, insurmountable. But there are a bunch of smaller tasks wrapped up into that. We need to make, a strong, sturdy material to make the capsule and the rocket out of. And we need to find a fuel that we can use that's powerful enough and compressible enough that we can use it for a rocket. And we need to find some kind of system that will be able to at least recycle some of the oxygen. And we need to find a system that can, control the spaceship in space. And we need to find a system that can tell the astronaut, what temperature the inside of the spaceship is. And we need some kind of system that relays power everywhere. And we need some kind of, there are a bazillion different tasks all wrapped up within that. And it seems overwhelming, but each of those tasks on their own is at least somewhat manageable. Excuse me for a moment. Sorry about that coughing fit. But yes, so they are in essence, engineers are technical puzzle solvers. And the other thing is too, let's say in this example, you get everything built and put together, you test it out. Well, it's probably going to fail the first time, and it's probably going to fail the second time, and the third time, and the fourth time, and the fifth time, and the 50th time, and the 100th time. And that's okay. You just pick yourself up, you find what needs to be fixed, and you figure out how you can fix it and try it again. Even when sometimes those setbacks seem pretty big. So what kind of jobs are there for engineers? Well, there are a whole bunch of different fields, including civil, which is the engineering branch associated with structure building, like bridges and things like that, and municipal centers, and systems like sewer systems and things like that, and traffic flow and all that kind of stuff. Mechanical, which is concerned with making machines. Electrical, which is, circuits and power generation. Chemical, making new chemicals. Aerospace, spaceships and airplanes. Structural, building big structures. Genetic, messing around with genes. Biomedical, drugs and prosthetics and things like that, medicine and prosthetics. Computer, how the hardware and software of a computer interact, and chips and things like that. Software, which is, the building of software and the design of them and everything. Military, so, not just machines of war necessarily, but that as well, but also, logistical things like, deployable bridges that can be built in 2 hours and stuff like that. Nuclear reactors. Forensic, stuff that can be used in a court of law. Reverse, taking stuff apart and seeing how it works. And then, environmental, and so that's the art, or excuse me, the science of, That's the engineering associated with structures and systems to uh, mitigate environmental damage and affect environmental factors and things like that. Uh, solar shades and cloud seeding and things like that. So don't think of engineering just as a guy in a hard hat. There are many different kinds of jobs, from hands-on to research to leading a team. But of course, there are some perks to the job too. I mean, it's not like it's cool to do it regardless, but engineering is a pretty good field to go into for, well, a couple of reasons. And one of them is money, as was evidenced by that silly little picture macro in the previous slide. Um, in this particular slide here, the sciences related fields already start out with a bit of a head start over things like business and healthcare and social science and agriculture and stuff like that. But engineering does actually rise above those as well. Like physical sciences starts out pretty decently, and computers and mathematics start out pretty decently, and they end pretty strongly too. But engineering is still, a pretty widely respected and highly regarded field. So $75,000 a year if you have a bachelor's degree, and about $100,000 a year with a master's. And these are median earnings, so this is the middle. This is not the lowest, nor is this the highest. This is exactly in the middle. Not an average either, so the average might be higher, the average might be lower. The mean, or the mode. These are the top 10 college majors that lead to high salaries. So as you can see here, pretty much all of these are engineering or sciences, mostly engineering. And then the light blue bar is, 10 to 15 years within a career, and the dark sort of grayish blue bar underneath it is the starting salary. So, you've got anywhere from $60,000 to $100,000, $60,000 starting to $100,000 mid-career for most of these, and then up there you got petroleum engineering being all fancy, starting at 100 grand, going up to 160 grand. But whatever. That's still, all of these are a lot of money. And then on top of that, you've got job and life satisfaction. So the percentage of college graduates sorted by major who answered satisfied or very satisfied to the question, overall, how satisfied are you with your current career path up to now? So this was a satisfaction survey. They asked these college graduates whether or not they were happy with what they decided to do. And as you can see, chemical engineering sitting up there at the top. Computer science is pretty high. I mean, some of these don't seem that high, but when you get right down to it, having at least a minor majority say that they're satisfied with what they decided to pursue, that's pretty excellent. Half the jobs created today are the result of technology. So you've got things like internet-related stuff, like search engine optimization and social media things and stuff like that. However, many jobs are being lost to technology. So a lot of these hands-on things are being lost to technology due to robots and things like that. So I believe this graph is about 6 or so years old, but regardless, it's a general trend over the last like 20 years or so of the shift in the job market. A lot of the medium skill stuff like production and office jobs and things like that are disappearing, whereas a lot of the high skill stuff, which is the management positions and professional positions, professionals being specializations like doctors and lawyers and things like that, and then technical occupations, those are all increasing at a similar rates to how much the medium skill stuff is decreasing. Now, it's not obvious. It's obviously not a one-to-one conversion, but it is happening. In this picture here, this used to be staffed entirely by humans on an assembly line, and now they've all been replaced by robots, and then the only people you see remaining are just some people here and there who are hired to basically man the robots and make sure that they operate smoothly and maintain them and stuff like that. So whereas those jobs were created in order to maintain the robots. The jobs of the people who actually made what was being made here, well, they no longer work there, unfortunately. So it's good to sort of future-proof yourself as well. Then we got the engineering versus the scientific method, and actually we're gonna just blow through this presentation today because we got like a couple of slides left, and then I can let you guys go. So this is the difference between the scientific method and the engineering method, and this is good for I mean, it just sort of illustrates the difference between the two. So the scientific method consists of observation, creating a hypothesis, experimenting, analyzing your data, coming to a conclusion, and having your peers review it, whereas the engineering method is researching, planning, prototyping, and commercializing. But what do these mean? Well, scientific method, observation, you take a look at something in the world and you go, huh, that's odd. You know, this happens. And then a hypothesis would be like, I think this happens because of this, or I think if I did this instead, this would happen. Then you experiment. You try to do the thing and see if the thing works out like you thought it would work out. You may not think it'd be like it is, but hopefully it do. Then you analyze the data. So you basically take a look at all of the times you attempted to do the thing and how many times it ended up doing the thing and how many times it ended up doing something different. And you come to a conclusion and you go, well, it happened enough that I think it's probably pretty reliable that doing this thing makes that thing happen. Or it might be like, oh, that doesn't work at all. I was totally wrong, in which case you might go back to your hypothesis and be like, okay, so I think it didn't work because there's this thing I didn't take into account. And then you go back through the process again. And you might get stuck in a conclusion hypothesis sort of loop for a while. Once you're satisfied, though, then you could send it off to peer review, in which case a bunch of other scientists would basically take your process and do it themselves and compare their results to your results to see if, like, you know, everything lines up. If it does, then they're like, oh, hey, that's probably pretty true then. If it doesn't, they're like, well, maybe something's different about the environment. Maybe you did something wrong. Maybe you falsified it, although that happens much less often. Well, certainly than it used to as well. But yeah, that's the scientific method. It's basically the way you arrive at a conclusion about something. Then the engineering method is research, plan, prototype, and commercialize, like I said. So researching is researching possible solutions to whatever problem or obstacle you have. So like, hey, I want to make I want to make this thing that does a thing. Then planning is like, okay, well, I have all these options to make this thing do this thing. Which one might be the best one? Let's go with this one. The prototype is, I made a thing out of things to do the thing that I want. Does it work? And if it does work, fantastic, you move on to commercialize. If it does not work, you move back to research. And so whereas with the scientific method, you have the conclusion and hypothesis loop, you have the research and prototype loop, or the prototype and research loop. With the engineering method, you might go back to the drawing board many, many times before you arrive at an answer that you're satisfied with. Or not an answer, but you arrive at a prototype that you're satisfied with. And then the commercialize is the tricky thing. Commercializing is when you make it so that whatever thing you made can be made on a larger scale and provided to the entire world feasibly. So to go back to an example from last semester, the whole thing about graphene. And, you know, graphene, we know that we can make it and we know that we can use it for stuff, but we can't really commercialize it yet because A, we're not really sure what we're going to use it for. We have a vague idea, but we're not really sure how we're going to use it. And B, we can't make it reliably and cheaply enough in large amounts. It's just not possible. So as it stands right now, it remains sort of an engineering and scientific marvel until we can reliably make it, mass produce it, and then it becomes a fact of life. But yeah, that is going to do it today. So just in case there's anybody here who's never been here before, the way we normally do this is I'll ask some poll questions at the end of the lesson. And I'm going to do that today just so you guys get familiar with how to do it. Those of you who've done it before, well, hey, free poll questions. You can answer whatever you want. Doesn't really matter. This is a pretty easy class. And then once I'm done with both of those poll questions, we'll leave it open to question and answer time, in which case you guys are more than welcome to ask any questions you might have in the question box or the chat box that you have on your little GoToWebinar interface. You're actually more than welcome to do that throughout the class as well. I actually encourage you to, because I like being able to see that you guys are responding and listening and stuff like that, and it's good for interaction and everything. It's nice to be able to talk to you guys while I'm doing this as well, so I'm not just talking at a monitor. Right now I'm actually pacing back and forth, standing in front of my computer because I'm sick of sitting or laying down all day. Don't ever get the flu, it's terrible. But regardless, yeah, if you have any questions about anything, you can always ask them then. They don't have to be related to the class necessarily, but whatever. If you don't have any questions, as soon as we're done with the poll questions, you're always more than welcome to head out, because I know you guys have a life and you got things you got to do, and you can't necessarily just be hanging around for another 15 minutes afterwards, like trying to just like patiently waiting for everybody else to make sure that they don't have any more questions. Like that's not, if you don't have any questions and we've already asked the poll questions, then everything's done. Just go ahead and head out. Otherwise, we'll go ahead and do this. We'll run through everything just like before. Once it's all done, you're more than welcome to head out. Have a wonderful weekend, and we will see you on Monday.